Oh, hi. I was just tidying up the office in anticipation of your visit. I guess I still have a little bit of work to do. But the main purpose of today's lecture is to figure out how we measure the basic properties of stars, besides the sun, in order to help us figure out how they work. What are the basic properties of stars? I really have just two that I want to keep track of. The first one is the temperature on the surface of the star, and we already learned in previous lecture that that's fairly easy to measure. All we have to do is look at the spectrum of the star, whether it would be the sun or a star that looks similar to the sun or stars that look vastly different from them. By measuring the spectrum, we see absorption lines that tell us what kinds of atoms in what ionization states in detail are present in the atmosphere of that star. That can give us a highly accurate measure of its temperature on the surface, which might be related to its temperature inside, which would be interesting. But the most fundamental thing, I suppose, that we really need to know about every star besides the sun is how much total power is it putting out. And I'm measuring that, for example, in watts. That's an awfully small unit when we're talking about stars, but that's energy per unit time, joules per second. And for the sun, you understand it's very easy to figure out what its power is. We just use the brightness formula. It's the inverse square law of brightness. So the brightness, of course, is the power of the star. You'll sometimes see this in a textbook called the luminosity of the star. I don't care whether you call it power or luminosity, it's watts. It's energy per unit time. It's something intrinsic to the star regardless of where we look at the star. Wherever it is, it's putting out a certain amount of watts. In the case of the sun, it's very easy. We measure the brightness of the sun as seen here from our distance, our vantage point on Earth. We are what, 93 million miles on average away from the sun, and so you remember the brightness formula, or say take 150 million kilometers, then you take an imaginary sphere of radius 150 million kilometers, you work out how many square meters that is, and you multiply it times the brightness of the sun, which is about 1,400 watts per meter, and you get a remarkable finding that the sun is putting out 4 times 10 to the 26 watts. Wow, thank goodness for scientific notation. Of course, it looks spectacularly bright, but that's only because it's very nearby. And the insight that Galileo and other people had, Kepler and so on, was that the other stars, which look so incredibly dim by comparison, are intrinsically actually comparable or even more powerful, more luminous than the sun. It's just that they're at such a high distance. So you see, it all gets down, this fundamental quantity of power, to knowing the distance of those stars. I know that they look very faint, the brightness is very small, but we have to multiply that by 4 pi distance squared, and we have to figure out how huge is the distance. And here's where this concept of stellar parallax comes in, which is exactly what Galileo and Tycho Brahe and these other early astronomers were desperately trying to measure. And as you recall, this is the reflex, the apparent reflex motion of a star, which might not be moving at all, as viewed by us on a moving platform. We're on the Earth going around the sun in an annual orbit. And so if I'm looking at a star over here, I'm actually not at the sun. I'm on the Earth, which is a moving platform, and I'm moving back and forth around the sun. And so the star, which is not moving, is going to appear to wobble back and forth with respect to more distant stars. So at least I ought to be able to measure the parallax of nearby stars. And yet, you recall that for hundreds of years, in spite of serious attempts to do this, the parallax was not detected. A real serious problem for the heliocentric, the correct model, if we're really moving around the sun. And the answer, of course, was this parallax is measurable with extremely high precision, but it's so small. Why is it so small? Let's look at the next slide. It's so small, it's such a small angle because the distance is so vast, even to the closest stars. This is a grossly not to scale diagram, but we'll look at it here anyway. Here is the Earth over here on one side of the sun in the summer. Here it is on the opposite side in the winter. Here we're looking at a nearby star projected in the sky against some constellation of distant stars. And as you can see, 6 months passes and the star has appeared to wobble back and forth with respect to the distant stars. So this wobble angle is called the parallax. We'll call that P. It's a very small angle. And then the long axis of this triangle here is D, the distance to the star. And for a small triangle, you see that the parallax angle is just this baseline. We have to know this baseline accurately. 1 astronomical unit. That's the baseline of our triangle. How far we are from the sun. There's the baseline. We have to take the baseline and divide it by the parallax angle. And this is really just the definition of angular measurement for small angles. This is the sine angle approximation that you don't have to bother about. Anyway, here's a really very accurate formula for the parallax. So if typical nearby stars were only a few hundred or a few thousand astronomical units away, in other words, if they were just lurking around in the outer solar system, these parallax angles would have been a reasonable fraction of a degree, and they would have been measured by Tycho. But no. In fact, the nearest star is at such an incredibly large distance that the angles are actually not measured in degrees. The parallax angles for the nearest stars are measured in seconds of arc. What's a second of arc? You take a degree, 1 degree, it's about that much of an angle there, the width of your finger, it's at arm's length, and you divide that into 60, don't cut your finger, and that 1/60th of that would be 1 arc minute. It's a 60th of a degree, and then you take that little arc minute and divide that into 60 little teensy angular pieces that are really practically too small for your eye to distinguish. That would be 1/3600th of a degree, or 1 arc second. And actually, the nearest star even has a parallax angle, it's Alpha Centauri, which is a little bit less than that. In other words, these stars are really far away compared to any other scales we've seen so far. Compared to anything in the solar system, even the nearest stars are vastly far away. Hundreds of thousands of astronomical units. In other words, light years in distance away. But fortunately, if you have good enough technology for very precise angular measurements, which has been perfected over the last 50 years or so, 100 years it's been working for the nearest stars, you can measure these small parallax angles now for tens of thousands, maybe hundreds of thousands of stars. There have been entire space missions devoted to measuring precise parallaxes for stars. If the star is too far away, it's really hard to do. If it's maybe tens of thousands of light years away on the other side of the Milky Way, parallax angle won't be measurable. But for many, many stars in the local part of our galaxy, this measurement has now been made with a reasonable accuracy, and then we know by simply measuring its brightness, we multiply by 4 pi distance squared to get the power, the intrinsic luminosity of the star. Great. Soon as you've got these two fundamental basic quantities of stars, the surface temperature, which we got from the spectrum, just analyzing the light, and then the power of the star, which we got from basically getting its distance, if we had the parallax. By the way, I just want to mention, this whole distance problem is one of the most fundamental challenges to astronomers, because we're looking at a two-dimensional view of the universe. We can't go out there, and we're trying to figure out three-dimensional information about the depth, the relative distances of objects, which may be incredibly different distances. You know, Mars looks, you can see that in the sky, and then you can see the star Sirius behind it. They look kind of similar. The distances are ridiculously different. So astronomers still, to this moment, are in a huge challenge to measure the distances of everything to get a three-dimensional view of the universe. But assuming that we can do that for nearby stars, what's the first thing you would want to do? Let's take the two quantities that are intrinsic to stars that we've measured, the power of the star and the surface temperature of the star, and let's make a graph of them and see if it's correlated. There. that didn't take a lot of scientific genius to figure that one out. You measure two quantities, put them on a diagram, see how they correlate. And the first astronomers to do this have, well, this Hertzsprung guy in Europe, it's kind of hard to pronounce, and then the American astronomer who's doing it at about the same time was Russell, and so since I guess they both did it independently of each other and published their results without knowing about it, we'll call this the Hertzsprung-Russell diagram. But I guess I would just like to call it the temperature luminosity or temperature power diagram, unless you're interested in the historical correctness of giving credit to all of the original discoverers. So you don't have to know their names, all right? I'm sorry. They're great astronomers, but this is not a history class. So what we find when we do this correlation here, for historical reasons, Dr. Hertzsprung and Dr. Russell plotted the surface temperature backwards on this axis. So they put the lower surface temperature, cooler stars on the right-hand side and the hotter stars on the left-hand side. I'm not even sure that they exactly knew that they were looking at temperatures when they plotted this. They were looking at different types of spectra. And then they got the vertical axis logically going from the lowest power stars up to the highest power stars in the top part of the graph. All right? I'm about to show you the data. Let me tell you, they put hundreds of stars, of nearby stars on this diagram, and you know what? The great majority of the stars had a very simple, rather remarkably tight correlation between these two quantities. How interesting is that? More than 90%, well, let's say about 90% of the stars actually that they could find lie on something called the main sequence. There are some oddballs that don't follow that path, but many of them do. Let's see if I can show you in the next slide. Ta-da! There it is. Here is a typical, well, let's see. This is the apparent magnitude of a cluster of stars in the Pleiades, and so what we have here is the brightest and therefore most intrinsically powerful stars are at the top of the graph. Unfortunately, it's a magnitude graph instead of just a graph of linear power. Anyway, these stars here are, what is that, 10 magnitudes. These are 10,000 times less powerful than these stars. On this axis, well, this is a little bit lazy. They simply measured the color of the stars as if they were perfect black bodies. They're not exactly, but close enough. And so, yes, the red stars would be the lowest surface temperature stars. Remember Wien's law? If their energy is coming out primarily at a long wavelength, that means a lower temperature. These stars down here have a considerably lower surface temperature than the sun, maybe 3,000 degrees centigrade. These stars here are considerably hotter than the sun, maybe 10, 20,000 degrees centigrade. But there are only a few stars. Yes, that's a real star up there. That's odd. There's a few stars down here. There's a few stars up there. The great majority of these stars all lie on a so-called main sequence. In other words, if you know the intrinsic power produced by the star, you can predict exactly what its surface temperature is going to be. One determines the other. Or if I told you, for example, this is kind of fun, if I told you, for example, that I had a star in the Pleiades that was right about here, that's about right, that color there, which sort of corresponds to white, that color corresponds to the temperature of a star of the same surface temperature as the sun. What the main sequence is saying, because the sun is also a good main sequence star, main sequence is saying, well, that star in the Pleiades, or I don't care where it is, that star, halfway across the galaxy, also has the same power output as the sun, 4 times 10 to 26 watts. They're, right? It's like peas in a pod there, solar-type stars. Whereas if you find a star which is considerably hotter on its surface than the sun, it's also going to be considerably more luminous. Gosh, that makes a great deal of sense, doesn't it? Because of what we learned from the Stefan law about thermal radiation coming from black bodies. These stars are, in fact, acting pretty close like good black bodies, and we learned the laws of radiation from black bodies in the previous lecture. All right, so we can compare these two observables then, the luminosity, or the power, and the surface temperature of the star, and we find this close correlation, which is the main sequence. And now I want you to think about this. Does this make sense? Yes, it does. What do you find, what do you expect when you have two stars? One is the surface temperature of the sun, and another star is, let's just take a concrete number here, let's say instead of the surface temperature of the sun, 5,000 centigrade, it's twice as hot on the surface. Let's say 10,000 degrees centigrade. I'm glossing over, in the book it often calls them degrees Kelvin. All right, but you realize that the Kelvin scale, which goes to absolute zero, is only different from the centigrade scale by 273 degrees. So I could be off by 273 degrees. Who cares? I'm talking about 10,000 degrees. So close enough. All right, so we have two stars. Let's suppose, just for the sake of argument here, suppose that the stars were the same size, meaning that they have the same radius, meaning that they have the same surface area, 4 pi r squared. They have the same number of square meters then. The sun and this hot star would look a little bit bluish. The hot star would. So, assuming that the laws of blackbody radiation, such as the Stefan law, apply approximately to stars, an excellently true assumption then, how much more total power do you expect is coming from the hotter star? Well, what does Stefan's law say? It says that power per unit area, watts per square meter, increases with what power of the temperature? Temperature, surface temperature, that's what we're measuring, to the fourth power. Wow. A hotter surface of the same given size is much, much more efficient at putting out thermal power than a cooler surface. So the hot star that's twice the temperature of the sun is putting out, let's see, 2 to the fourth power. That's 2 times 2 times 2 times 2. 16 times more energy per second per square meter than the sun. So if it has the same size and the same number of square meters, how much more luminous is the hot star going to be compared to the sun? 16 times more luminous than the sun. Wow. 4 times 10 to the 26 watts times 16. 64 times 10 to the 26 watts. That's a powerful star. And in fact, there are quite a number of these stars out there in the local neighborhood of our galaxy. And there's actually even more stars which are, say, only half as hot temperature as the sun. And those stars, being only half as hot on their surfaces, would have what? 16 times less power than the sun. Well, what I just described to you is very close to what you actually observe in the main sequence. Not exactly, but very close. So I think we have a tentative, simple explanation of what the main sequence is. Well, so my previous diagram here, slide, says, what is the cause of the main sequence? Well, my simple answer is, I guess the cause of the main sequence mainly is most of those stars are roughly about the same size. Actually, the stars that are hotter than the sun are even more luminous, more powerful than T to the fourth by a little bit. So they're also a bit bigger. They have a bit larger radius and surface area than the sun, but not by much. So I'm not going to worry about that one too much. The main reason for this nice correlation of star temperature with star power is that they obey Stefan's law for black bodies of a fairly comparable size. But that isn't really the fundamental answer. Okay, that's interesting. So why are all stars, not all stars, why are all main sequence stars, that's a majority of stars, a fairly similar size to the sun? What determines their size? That's a deeper question. What's the underlying fundamental cause of this? I'm just going to tell you the answer right now and then explain how the difficult chain of argument, how we figured out logically this answer in a few minutes. The answer is that these different stars at different locations on the main sequence differ in one most fundamental property, which is their mass. That means how much gravity the star has, how much stuff it has, how much fuel it has to power it. So the mass of the star is the absolutely most fundamental property, if we could measure that, which determines all these other observables that we have been going around measuring. Well, we've been collecting a lot of measurements of power, we've been collecting a lot of spectroscopic measurements of temperature, and we find, though, that those are largely determined by the mass of the star. That's harder, though. These stars don't have little mass stamps, 10 kilograms, 10 to the 30 kilograms stamped on them. We're going to have to make some much more difficult measurements than the ones I was describing before if we want to weigh a star. Now, a lot of this course, you'll notice, is looking at the effects of gravity so we can weigh things and determine where the masses are in the universe. Well, here's the first example of this. It basically goes back to Newton's laws, even Kepler's laws. So, as I said here, the mass of a star is the most fundamental property that controls everything about its life, particularly when it's on the main sequence. How am I going to measure that? How do we know, for example, the mass of the sun to very high accuracy? Bing, that's right. If you said we know how much the mass of the sun is by measuring the orbits of our planets around it, so we can see how much they're accelerated by, and we use basically the Newton version of Kepler's third law formula. Remember, it has that 4 pi squared on top, and then it has gm1 plus m2, where m1 is the mass of the sun underneath. And so, in other words, the more the mass of the star is, the shorter the period of objects orbiting around it will be, because they're being accelerated more. So that's how, using Newton's laws of gravity, that's how we figured out the mass of the sun to high precision. Darn, very difficult to study planets orbiting around other stars. In fact, that's only started fairly recently. We could send a satellite out there and watch it orbiting around the star. Unfortunately, that's beyond our current technical capability, and you'd have to wait hundreds of years to get a result radioed back to you. Do we have any natural experiment where the universe is producing these situations for us, where there's a test object orbiting around a star that we could watch? Yes, there is. Hooray! They're called binary stars. And I'm happy to say that the universe has provided our galaxy with loads of binary stars that we can study in relative ease. So we can watch, well, what do we watch when we actually see a binary star? That means that there are two stars held together by their mutual gravity. There's an example. I picked Sirius because it's very famous. There's Sirius A, the bright one. There's Sirius B, the dim one, which is much dimmer. Here's a photograph of them in 1900. Oops, I shouldn't change my slide here. There's a photograph in 1910. They seem to be in a slightly different orientation. Oh my gosh, by 1920, that little dim one was over here. 1930, it's up here. 1940, it's on the other side, and so on. So it's a visual, or photographic, or whatever, binary system with a little star and a big star, or a faint star and a powerful, luminous star. Well, clearly something is going around something. What do you think it is? The correct way of looking at this, which was worked out by Newton, he realized that his laws of gravity required it, is that it's not correct to say that the little star goes around the big star. If it was a really little star, like suppose it was Jupiter, that would be a good approximation. I mean, it's a pretty good approximation to say that Jupiter just orbits around the sun. But if Jupiter were a bit more massive, you'd realize that's not exactly the right approximation. What actually happens in our solar system is all of the planets, including Jupiter, orbit in elliptical orbits around the center of mass of the solar system. Now, the center of mass of the solar system is very close to the center of the sun. It's not in the middle of the sun, though. It's a little bit, thousands of miles away from the center of the sun, still inside, under the surface of the sun, mostly in the direction of wherever Jupiter, and then to some extent Saturn, are. So that, yes, so the sun actually also orbits, or wobbles, I should say, around the center of mass of the solar system. But if you had So that's tough to measure. But if you had a fairly substantial binary star, like Sirius B here, which I believe is a white dwarf star, that has a fair amount of mass, then what you would actually see very clearly is both stars are orbiting not around each other, they are orbiting around their common center of mass. How do you find out what the center of mass? Well, all right, so here's the formula we're going to apply. I mentioned this already. We measure the orbital period. That's not too hard to do. This is a little bit trickier. We need to know what the separation of the two stars is. And if we could measure those, well, basically what we could get here is at least we could get the sum of the masses of the two stars. So what you really want to do here is you want to measure the orbital speeds of the stars. Best way to do that would be to measure their Doppler shifts. And as we found out, one of the easiest things you can ever measure, because stars have all these very easy to measure absorption lines at fixed intrinsic wavelengths, it's very easy to see if that pattern of absorption lines has moved to the red or to the blue a little bit as the star goes away from us or comes towards us or goes away from us in its orbit. So we can measure the orbits of binary stars to figure out their masses. Where is the center of mass? This is the basic deal. If you had two equal masses, then just think of two equally heavy people on a seesaw, then the center of mass would be halfway in between. That's exactly what happens if you have two stars of equal mass. Picking up just where I left off in mid-slide, we saw that Newton's third law means that planets actually don't orbit exactly about the sun, but they orbit about the center of mass of the system, because the sun is exerting a force of gravity on the planets, and the planets are also exerting an equal and opposite force on the sun. That's Newton's third law, the action and reaction, the force and the opposing force. And this also applies then to binary stars. The binary stars orbit not each other, they orbit around their common center of mass. So in a realistic situation, one of the binary stars might be, for example, twice as massive as the other. So here's an example, just so you can see where the center of mass would be. Let's suppose that this corresponds to a star with twice the mass of this star. Then you can see that the center of mass will be about a third of the way between the massive star going over to the low mass star. And what that means then is that the massive star will execute a small orbit. Small radius, just 1/3 of the radius of this star here, which will be on a big orbit because it's the low mass star. In other words, even though it's a little bit of a confusion people have sometimes about Newton's third law, yes, the forces are equal. The force of A on B is equal to the force of B on A in the opposite direction. But this does not mean that the accelerations are equal. No. The low mass object accelerates much more. It's proportional to the inverse of the mass, and that is also true for binary stars. So the low mass star is going to have proportionally more acceleration than the high mass star, and this applies universally, whether it's a pair of stars or whether it's some planet going around a star. The rule is the same. And so we can use that now if we can study the motion of binary stars. Now I showed you an earlier example, a case of Sirius, it's a very nearby star, where you can actually see the two stars if you were willing to wait long enough. After decades, patiently, you can see photographs are showing that the two stars are indeed going around the center of mass. And the more massive star isn't moving very much. The low mass star is moving quite a lot because it's accelerated more. What if, though, a more typical situation is you have binary stars? Like I said, they're not at all uncommon throughout our galaxy, but they're so far away that your photograph just makes it look like a single point of light. The two images, the light from both the stars, is merged into a single unresolved point of light. This is the most common situation. So if you just look at it with a picture, it looks like a single star. Are we out of luck? Don't worry. Spectrographic information comes to our aid here. We can spread the light out and look for the absorption lines in what looks like a single star, and if it's actually the combined light of two stars, we are going to see what? We're going to see two sets of absorption lines from the light of each of the two different stars that's there. There'll probably be usually similar absorption lines. If the stars are quite different temperatures, they could have different sets of absorption lines. But here's the point. We can tell them apart because these two sets of absorption lines are not always right on top of each other. And why not? Because they each have a different Doppler shift as seen from Earth. That's the key to this. Here we are on Earth over here, and here, well, this is not a very good drawing. There's a massive star here, A, and then there's a smaller star, B, and at one time in the orbit, I don't like this diagram very much, B is going to be coming at us, meaning a blue shift. At the same time, the other star, the companion, is going to be redshifted, moving away from us. That's how an orbit works. This one's coming towards you, this one's going away. Then they're at the same velocity, so the lines will cross over. Now this one is redshifted and this one is blue shifted. Then the lines come together. So the spectral emission lines are momentarily on top of each other, then they're shifted this way, then on top, then that way, that way. So if you just have the patience to take a series of spectra, which I've done and many people have done, you could determine that actually that light that looks like it's coming from a single star, it's actually the combined light of two stars in a binary orbit around their mutual center of mass. And the beauty of this is, of course, one of the stars will shift more in general, have bigger velocity shifts, while the other one is shifting a little bit. The one that's shifting a little bit is the high mass star. It's accelerating less. So you can actually get the ratio of the masses of these two stars, and of course you can get the period of their orbit. In other words, you can, since you know the ratio, and then from the previous formula of Kepler's third law, explained by Newton, you get the total mass. Basically, with a spectroscopic binary system, by studying the motions of the two stars, you can work out both of their masses. Pretty neat. We're not going to go there and measure these things. This is all done at distances of trillions of miles. So it's a very clever accomplishment that the spectroscopy of stars gave to astronomers, the ability to weigh the stars by watching them accelerate each other, according to Newton's law of gravity. This is very clever. And in fact, this is such a powerful technique, I'm just going to mention this right here. It's going to come up later in the course. What if we had a binary system where there are two objects orbiting the common center of mass, and one of them was virtually invisible? Well, like a planet is virtually invisible, or even something bigger. Could be a very dim star, like a white dwarf. Or it could be something that's virtually totally invisible, like a collapsed star, like a neutron star, or something even more exotic, such as a black hole. In that case, would you know that there were actually two objects there? What would that look like? There's only light coming from one object, so you just see this one object. But it would be quite distinctive if you were to take the spectrum and measure the Doppler shifts. You would notice something odd, that it's periodically coming towards us, stopping, going away from us, coming towards us, blue shift, no shift, red shift, no shift, blue shift, and so on. You would notice that it must be in orbit around an unseen companion. It must be there because something is going to cause that star to accelerate back and forth. Something is changing the Doppler shifts periodically. You could measure the period, you could measure the velocity, and if you were willing to make a guess about the mass of the star that you see, try to make an educated guess, this is fun, you could infer what the mass of the unseen dark companion would have to be big enough to accelerate the star that you see. This is a so-called single-line spectroscopic binary, where there's only one set of absorption lines, but it shows clearly that there are two objects in a binary orbit, and you could work out what the mass of the unseen object is by measuring its gravitational acceleration on the seen object. Brilliant method, which is of enormous significance to our field. But anyway, there is one little detail about this that I'll just lay on you for right now. It's not terribly important, but you can see all of my diagrams here are assuming that all of the orbital motions of these stars are in the same plane as Earth. In other words, the orbital plane lies along the direction to the Earth. In other words, I've been assuming here for simplicity that we're viewing this orbital plane of stars edge on, like this. That way, when they're coming towards you, you're seeing the entire approach motion, the full blue shift. When they're coming away from you, you see the entire redshift of velocity. But of course, that is only true. Remember, Doppler shifts only measure whether things are getting closer to us or further away from us. They do not measure sideways motions. So, for example, what if you had a single point of light, which actually was two binary stars close together, and they were orbiting in this plane? You're the Earth over there. They're orbiting like this, like this. So the velocity, they never get closer or further away from you. The velocities are always sideways. They're in the plane of the sky, like that. Would you see any Doppler shifts? No. There are no Doppler shifts at all. You'd have to be on a planet up there. You'd have to be an astronomer over there to notice any Doppler shifts. You would see just this constant velocity. The lines would never move because all of the motion is in the plane of the sky. In other words, now in an intermediate case, let's suppose that the orbit was tilted like about 45 degrees. So they're moving like that. So yes, they do get closer and further away from us. We would see periodic blue shifts and red shifts, but we wouldn't see the full blue shift and red shift. We would see less than there really is. Well, if we didn't take that into account, we would at least have a lower limit on what the total mass of these stars is. So by assuming that the stars are edge-on, then at least we're getting a lower limit to their mass. If the orbits are not seen edge-on, then the masses could be even larger, and we're just missing some of the orbital velocity. All right? Thinking, oh God, what a nuisance is that? Who wants that kind of hassle? Don't worry, relax, Astro 4 students. There is one golden situation where we can be absolutely confident with 100% certainty that we have found a binary system which is viewed exactly edge-on, which is what we want, to get the exact masses. And what would that be? Two stars which are moving around exactly in the plane that the Earth also lies in, our viewing plane. We see them exactly edge-on so that one star periodically moves in front of the other star. And then halfway around the other side of the orbit, the other star blocks the light of the first star. That's called an eclipsing binary system. And that is like pure gold. That's a gift from the heavens, because that allows us to figure out everything with no questions whatever. We can measure the velocity. And this, by the way, you don't have to be able to tell directly that there's two stars there. Remember, these are so far away, it'll just look like one star. It'll look like the light from one point of light, except that periodically the light will dim. Why is the light dimming? So here's the light from both of the stars. This is time moving along the x-axis, and the vertical axis of brightness of the star. We're seeing both the stars. Just looks like a single point of light. But now notice, the little star moves in front of the big star, and so now these stars are opaque, so we've covered up some of the light of the big star, the red star back there. It's covered up. So we're not seeing as much of the red star there. So the total light of the system drops down, makes a little eclipse. All right. Then the orbit goes around. We see the light of both stars. Now the little star is on the other side. Whoops! What's happening here? At this point in the orbit, halfway around the other side, the little star is behind the big star. And like I said, stars are opaque, so we don't even see the light of the little star. It's completely covered up by the big star, so at the bottom of the eclipse, we're only seeing the light from the big star, and that's all. And then the little star comes out from behind, and we can see both of them again. So we see two eclipses. One star is getting blocked, and then the other star is getting blocked. And this happens every orbit, an eclipsing binary star system. But of course, it can only happen if these are perfectly inclined, exactly edge-on, so that we can see them. We can see all of the Doppler velocities. Now, there's a bonus to this. So first of all, we can measure the Doppler shifts and use Kepler's third law. Because of Newton's third law, we can figure out exactly the masses of both stars quite accurately. In fact. This is how we get real accurate masses of stars. But what is another fun thing? We can see how long it takes for one star to move behind another star. We can measure the duration of these eclipses. And since we know how fast the stars are traveling relative to each other, that gives us a size. Yes, we can get the diameter of stars. Even though they're way too far away, you would never be able to actually resolve them. You'll never see little disks of light like this. You'll never see 2 points of light. You'll actually just see one blob of light, but you can infer the size of the stars, the radius and diameter of the stars, from the length of the eclipses when they block each other. Bloody clever, those astronomers that do this stuff. A lot of this work was done at UCLA by a colleague of mine, Dan Popper, and it is the most reliable way we have of knowing both the masses of individual stars, if you're patient to do this, and also the sizes of individual stars. And that is the key information if you want to figure out what is going on inside the centers of stars, which we'll talk about next.